Hey everyone, in today's video we are going to determine the equation of the least squared regression line using technology or a calculator. And so the technology is actually a computer output, assuming we're using some program like R or something. So the other objective here is to use a residual plot to check for linearity. So that'll tell us whether or not regression lines actually apply. So I've got a set of data here. We've got our x variable and our y variable. So these are the actual amounts. And from this data set, we are going to try to calculate the least squared regression line. And I'll show you kind of why it's called the least squared regression line as well. So for this data, one thing you could try to do to get the least squared regression line is just kind of sketch the line that looks like it's going to capture all of these points. So actually, let's start with like a bad line. One guess that I could have made for our regression line could have been like this. Maybe I made my line look like this. And so it's possible that that's where the regression line is going to go. So hey, I just want to kind of give you an idea of what this name means, the least squares regression line. So whenever we do put this data into our calculator and try to find the equation for it, this is what's happening, right? You guys remember residuals? Residuals are the distance from the predicted value to the observed value. And so your least squared regression line is taking this distance and kind of assuming that it's a square. It's squaring the distance from your point, from the actual point to your predicted line, and it is going to try to minimize that. It's minimizing the squares. It's minimizing the area of all of these squares that I'm drawing. So you see on this line, I've got these massive squares here and here, small one here. So if I summed up all these squares, would that be the smallest possible value for that sum? So maybe I should write that out in words. What is the least squared regression line doing? The least squared regression line, it minimizes the sum of the squared error. So the error is essentially the residual, and then we're squaring that. So the distance from your actual point to your predicted point squared. That's the purpose of drawing the squares here, just to give you kind of a visual. We want the smallest possible sum of squared error. And luckily for us, our calculator is going to do that. So if you go to your calculator, turn it on, and let's enter this data into our list. So to get there, you'll hit stat, enter, and in list one, I've got 1, 2, 2, 4, and 6. For list number 2, I have 2, 2, 1, 3, and 5. Okay, hey, so to graph this, or not to graph this, to find the equation, we are going to go to stat, scroll over to calculate, and we are doing option number 8, linear regression, a plus bx. And I'm only choosing this option because that's what the AP exam is going to use. This is more like for algebra 1, right, with the mx plus b, but we're using a plus bx. So anyways, hit enter, and it's asking you, what is your explanatory variable? That does matter for linear regression. What variable are we predicting? In this case, it's just y. We want to count each list, not worry about that. You can store the regression equation. I'll show you where in just a second. But anyways, go to calculate. It'll give you the values for A and B. And you might even see like the correlation pop up. So our slope is 0.5375. Okay, so I'm just going to kind of go like this. A is approximately 0.54. Our y-intercept is 0.54, and our slope, again, I'm just getting this value from the calculator. It is, I'm going to round that one to 0.7. Slope is approximately 0.7. We don't need to worry about the other two values for now. So our regression equation, the least squared regression line, the line that's going to minimize this squared error, is y hat equals 0.54 plus 0.7x. That is the line that's going to pass through these points and minimize this amount of error. It's going to minimize the sum of all of these squares that I tried to sketch earlier. And hey, so what we'll do is graph this just to get a better look of, like what's going on. So hey, if we go to y equals, we can type in our regression equation. So if you remember where it said on, whenever we calculated this, it was asking us if we wanted to store our value anywhere. And so you could actually store this into your calculator to graph the actual regression equation. So I suppose we could just do that real quick. So let's store the regression equation. Go back to stat, calculate linear regression. That way we can plot our least squared regression line. Hey, so on store reg EQ, hit vars, and then scroll over to vars, scroll over to y vars, and we're storing a function. So hit enter, and it's asking you where you want to store your function. And so hey, we'll just do this one in y1. Hit enter, and then go back to calculate. Fantastic. So hey, when you hit y equals now, your regression equation will already be plugged in for you. So the benefit of storing it like this is that it's not going to do any rounding. It'll be the actual regression line, which is a good thing. Now, I want to plot all of this to give you a really clear picture of what this regression line is doing. So hit second and go to stat plot. We want this plot to be on. Plot number one, we want it to be a scatter plot because we're doing two quantitative variables. Everything else looks good. Awesome. If you go back to y equals, make sure this plot is on as well. Just the equal sign there should be like bolded or highlighted or something. So now that we've got all that stuff squared away, hit graph, and that's what it looks like. If you don't see it, hit zoom and then go to option 9. It'll make a perfect window for you to really analyze this perfectly. All right, so that is what the regression line is really going to look like. That is going to minimize our squared error. So it was much better than just this line here that I kind of just randomly sketched. Okay, so let me put that on here and I'll try to draw a couple more squares. So you see that I'm just a little bit below this point, like that. And then I kind of just go above this point. Just trying to do this freehand as best as I can, or not freehand, but just with the ruler. Here, so this is my regression line. Okay, so once again, this regression line minimizes the size of these squares. So you see like this one, the squared error there is like almost non-existent, whereas here I had this squared error. This one is just about the same size. Got this squared error. I've got some squared error right here. Got 1 unit away. This one is still very, very small. And this one, the size of the squared error of our prediction right here went down a lot. So hopefully you can see that, or at least have an understanding of what the least squared regression line does. That's literally all it's for. Minimizing the residuals, minimizing the squared residuals. Just a good way to kind of think about it. All right, so for determining the equation, that's really it. For your calculator, you just put them into lists, go to calculate, and then it's option 8, lin reg, and then in parentheses it goes a plus bx. So I'm gonna show you what it looks like when it's done from a computer, just some statistical programming software. Let me go here. And so here's this problem, right? Panel of judges rating the taste of different brands of potato chips. Somebody noticed a linear relationship. It has to be linear, of course, to do linear regression. So that's good. Here's a computer output. So there's a lot of statistical software. One is called R. It's like literally the name of it. It's open source. Another one is called Minitab. There's others that we don't really need to worry about. All you need to be concerned with is when you're given an output from a computer, be able to come up with the regression line and then, using it. So here's what you do. We can ignore a lot of this for now. The thing that you're going to focus on is the coefficient column, this thing right here. That's going to give us everything we need to come up with the regression equation. And so we are going to use this model to predict the rating of a brand. So we're predicting the rating, based off of bag, right? Fantastic. So the constant, this row, that will give you the value for A. Price, or whatever variable that they used, is going to give you the slope. Okay, depends on the variables used. So I guess to interpret this right, like if the price increased, we would expect the rating to increase by this amount. So anyways, let me just like write the equation out. So the regression equation for this situation is going to be negative 0.39 plus 2.52 times the price. The variable that they used, or the explanatory variable that they used, was price, okay? So then use this model to predict the rating of a brand that costs $3 per bag. So our predicted rating would be negative 0.39 plus 2.52 times the price of that $3 per bag. Okay, so I'm just gonna do that on my calculator. Negative 0.39 plus 2.52 times 3. All right, and I got 7.17. So the predicted rating would be 7.17. The predicted rating. We would expect a bag that costs $3 of that brand of chips or whatever to have a rating of 7.17. And hey, this just told us to round our answer to the nearest whole number. Okay, so I'll do 7. Fantastic. All right, let's just do one more. So what are we doing this time? Teresa was researching sales figures for popular video games. She wondered if she could predict a game's global sales based on its sales in North America. So the explanatory variable is North America, and they are predicting the amount of sales globally in a random sample of games. Here's a least squared regression analysis of her data. So remember, the only column that we really need to be concerned with to create the regression equation is this one. First column is just going to say COEF. So the regression equation, what are we trying to build here? What are we trying to predict? Again, we're trying to predict the global sales. So I'm predicting global sales. That's going to be equal to, so the y-intercept comes from the constant. The slope comes from the explanatory variable. So the constant here is 0.744 plus 0.497 times the North American sales times this variable. This will be the variable that you put in there. Okay, so hey, let's see if that option is down here anywhere. 0.77, predicting the global sales, plus 0.497 for North America. So that's it. That's how you interpret a computer output. It's a question that's going to come up pretty often, honestly, on the AP Stats exam. All right, so the last thing that we need to talk about here real quick is the the residual plot. So content from second camera. Here we go. All right, so going back to our list that we did earlier. So hey, a residual plot. We need to use a residual plot to check for linearity. So it's really easy, honestly. Residual plots. So what they do is, obviously, like they make a plot and make a plot. So we're graphing the residuals. I have to write that out as well. So we are graphing the residuals. against the least squared regression line. So what I'm saying is the y-axis, that will be your residuals. That's going to be the value of the residuals. And the x-axis represents your least squared regression line. So here's what they look like. Again, the y-axis, the residuals, and then right in the middle of it, you're going to see a line coming out this way. And that is going to represent your least squared regression line. This is the x-axis in a residual plot is the least squared regression line. The y-axis are the values of your residuals. Okay, so hey, for this first point, you see how it's just a little bit more or a little bit less than 1 above our least squared regression line. In fact, there's an easy way to do this on your calculator. Here, turn it on, go to stat, hit enter. So for list number 3, we are going to calculate all the predicted values. So scroll up to list 3, hit enter, and it's asking you, what is list 3 equal to? We're going to use our regression equation. So list 3 is going to be equal to 0.54 plus 0.7 times our x value. So our x value, remember our x value, the 1, 2, 2, 4, and 6, that's stored in list number 1. So just hit second, and then you could do 1 down here, and close your parentheses. So it's going to calculate the predicted values using our least squared regression line. So here's all the predicted values, okay? And remember the residuals, so we need to go over to list 4 and hit equals. The residual or residuals are the actual amounts minus the predicted amounts. So for list number 4, you can type in list 2 minus list 3. So here's going to give us all of our residuals. So we can see, without guessing now, that this point, the actual amount here is 0.76 units above our predicted amount, okay? And so, gosh, that's it. Those are the residuals for each point. So I could go like, I'll just use 0.5 for my scale on the residuals. 1.0 and 1.5. This will be negative 0.5. 0 goes in the middle. That would be a perfect guess. Negative 1.0 for this, and negative 1.5 here. All right, so hey, least squared regression line. I've got 1, 2, 3, 4, 5, 6, 7. My x, my inputs, I never exceeded 6, so I'm going to kind of follow that same format. 5, 6, and then I'll include 7 just for fun. All right, so when the x value was 1, I have a residual of 0.76. So I have a residual, a point will go about right here. And then my next residual, when x is equal to 2, I have actually 2 residuals, right? I have a residual here at 0.06 and at negative 0.94. So I have something just slightly above my regression line, something quite a bit below my regression line. And then the next x value I have is 4. The residual at 4 is negative 0.34. 0.34, so maybe like around right here. Give us kind of close. And then my last residual is when x is equal to 6, at a residual of 0.26. So about right here probably. Okay, so hey, that is a residual plot. Again, you just take a regression line, use that as the x-axis, and then plot each point's residual. How far above or below the regression line was it? So to use regression, to use linear regression, least squared regression, to use least squares regression lines, to use LSRLs, residual plots, Residual plots cannot show patterns. Residual plots cannot show patterns. So what I'm saying is, like, if we had a residual plot that looked like this, we had a residual plot that looked like this, where it had some points below it, they started coming above it, and then it started to go back down. You know, like we have this just peak of data. Least square regression lines are not going to work for a situation like this. So if it ever looks like this, don't use least squared regression. Don't use least squares regression when it looks like this. When the residual plot shows a pattern, you can't use least squared regression lines. One more thing, the data needs to be evenly spread. It needs to be evenly spread. So what I mean by that is, I'll just sketch one more thing for you. Like if I made a least squared regression line and I had like a couple points above the least squared regression line, but a majority of them were below the regression line, that is also not good. We are constantly over predicting the data, which is, again, a bad thing. So you need to have about the same amount of points above the least squared regression line as below it. And that's kind of the case here. We had 3 points above it, one was like almost equal to it, and then 2 below it. That's okay. All right, so yeah, I'll just show you one more thing, building off of this residual plot. So I'll just go back here. And so it's really easy to kind of guesstimate what residual plots look like. So like this least squared regression line, I have 2 points that are above it, and then I go to 3 points that are quite a bit below it. So it looks like this matches it pretty well. You guys see that? 2 above it, and then I go to 3 below, and then everything else was above my residual plot, or my regression line. Okay. Then this one, this graph displays a residual plot that was constructed after running a least squared regression on a set of bivariate numerical data. What can you conclude from this graph? When x equals 3, it's saying the least squared regression line, the least squared regression equation, underestimates y. So we predicted, remember these are our predicted y variables. We're predicting it to be here, but the actual observation was here. So that's true. It underestimated it. Our estimation, our prediction was below the actual value. And then for overestimating or underestimating, it looks to be about evenly spread about the regression line. And then the slope of the least square regression line is 0. We can't tell. We can't tell from our residual plot. Fantastic. So we can try one more. So for this one, does it appear to be a linear relationship between x and y? And so we start off with all of our points below it. Then you can kind of see this pattern where it's constantly underestimating. So honestly, this one's kind of tough. I'm going to say that they're, well, I don't know. I expect to like have some of these things lower the further along that we go. So I don't know. I'm going to say no. We'll see. Fantastic. There does not appear to be a relationship. There's a pattern here. It started with we were constantly over predicting the data. And then over here, we started under predicting the actual values. All right, guys, so that's going to do it for this video. Thanks for watching. Good luck on your assignment. Okay, bye.